Okay, greetings aspiring scientists. Welcome to today's video. Today will be my lecture on atomic theory, which is generally including past various theories of how matter was and existed and behaved. So there's actually a lot of theories that we will learn that we now know are no longer true, or at least parts of them are no longer true, but I think it's really important that we understand how the theory evolved and what pieces of evidence led us to throw out certain parts of previous theories. Alright, so we'll go to my slides here. This is structure 1.2 from the IB curriculum, the nuclear atom. So we have a guiding question here. How do nuclei of atoms differ? You maybe don't know what this word nuclei means. It's the plural version of nucleus that you probably have heard of, which is the central part of an atom. We will discuss what it is composed of and what its properties are. But hopefully by the end of this topic, you'll be able to answer this question fairly well. How do the nuclei of different atoms differ, and what properties do those differences relay to the atom? Alright, so the first section here is 1.2.1, the structure of the atom. So atomic structure. Now, early theories on what matter was composed of were probably almost everything you can imagine. Different elements like water and fire, or different degrees of consciousness, or different compositions of hot and cold, as if those might be elements. Almost anything you can imagine, people had an idea of what composes matter and the universe. But there was very little evidence for any of these theories that was actually found. So if we take one example, the earth, wind, fire, water theory, everything is made up of some proportion of these. For example, a tree might be proposed to be 70% earth, 15% water, 15% wind, or something like that. But no one was ever to actually isolate these elements and prove that they could be converted from one form to another in any logical sense. So that theory had to be thrown out or evolved. One of the earliest ones that did have some real evidence was when John Dalton, scientist, came along, started doing different measurements on different materials and substances. So here I have an equation shown. Oxygen atom plus hydrogen atom goes to water molecule, HO. So oxygen atom O, hydrogen atom H goes to OH. Looks kind of strange, right? Because you know that water is H2O, two hydrogens. But at the time, scientists and John Dalton didn't know this. But the important thing is what's at the bottom, the mass units. So he found consistently that when there was 16 mass units of oxygen, for example, 16 grams of gas, and there was 2 mass units of hydrogen, for example, 2 grams of gas, that was a perfect ratio for all the gas substances to react and disappear and form water. So he would get 18 mass units of water, which he predicted was some kind of formula of HO composed of the 2 gases which had unique properties, hydrogen and oxygen, and now they would form liquid water, which everyone is familiar with. But a couple things were shown here. First, there is conservation of mass. All of the mass that we started with, 16 plus 2 is 18, had to be completely in the products, so 18 grams of water had to be formed, and he consistently proved this. There is conservation of mass through chemical reactions. He also showed that the reverse of this can be possible, I think. So you can put in some energy with electricity, for example, to separate oxygen and hydrogen from water, and you will get, if you started with 18 grams of water, you'll get 2 grams of hydrogen and 16 grams of oxygen. And he also showed that through various experiments with hydrogen and oxygen, they could not be broken down anymore. You could try to zap them with electricity or heat them up very hot, and they would not break down into any smaller particles. I think you had to be careful though, because if you just heat up hydrogen, H2 that we now know is the formula of hydrogen gas in an open atmosphere like this, it will combust and burn and might look like you've broken it down. So it had to be, I think, in a concealed container, an environment where it was, he tried to break it down and was not able to. So this is good evidence that oxygen and hydrogen are pure elements that cannot be broken down chemically, but they can react together to produce a product where there is conservation of mass, and they are seemingly stuck together or bonded together in some way. Now, I don't think him or any scientist at this time really knew the shape of what these atoms were proposed to have, but maybe a sphere and a circle makes sense because, I don't know, soap bubbles and planets and moons and stars are spheres, so why not atoms as well? Alright. So I just want to take a moment to discuss something called physical paired systems. I don't know if it's actually called that. This is just what I'm calling it. But in chemistry and physics, we see a lot of paired systems. For example, charge, electric charge, it's split into positive and negative. Magnetism, split into north and south poles. Quantum spin, this is split into up and down spin. Wave phase, split into in and out of phase. You may not know what that is, but you probably will after you studied physics. Spin as well, we'll discuss a little bit in this class, but really nobody knows what spin is in high school, even the teachers, I don't think. Anyway, so these are all human codings with not much true meaning. The important thing is that two opposite states exist, and they are exclusive to each other, and they have unique properties. So we'll often color these with like red and blue and put a plus or a minus or an S and an N or an up and a down on these. But just be aware that humans just decided that's a good way for us to visually distinguish them. The important thing to realize is just that there are these two states, and something can only be one or the other in most cases. So why do I bring that up? Because it's time to talk about electric charge. So there are two types of opposite electric charge. They are positive and negative. I'm sure you've heard this. I'm sure you've seen it on your batteries. So some objects have no net charge. This is possible if they have a balance. But positively charged objects feel a repulsive force away from other positive objects. Really important idea. The same is true for forces between negative objects. They feel a repulsion. However, positively charged objects feel an attractive force towards negatively charged objects and vice versa. So I have a little diagram here showing that. Negatives repel, positives repel, but positive and negative attract. Okay, so what was next? I think it was quite a few years, but scientists had been doing work on electric charge and current and voltage, and working with various substances. So I think the scientist named J.J. Thomson was the one who really discovered what we call the electron. Now this experiment and apparatus is very complex, and I think you should come back and consider this instrument after you've studied the physics curriculum and the chemistry curriculum in IB. But I'll try to briefly explain what's going on here. So this device, I believe, is a mass spectrometer. And there are several different parts to it. Starting on the left, we have a cathode ray tube. So scientists, I think, were aware of various different types of radiation. They probably knew about visible light, ultraviolet light, infrared light, maybe X-rays, microwaves, those kind of things. Maybe also knew about alpha particles or some other different types of nuclear radiation. I'm actually not sure if that was known at this point, but various types of radiation were known. And some parts of electricity were known, I think. So they knew about like static electricity. Things could attract or repel each other when they were rubbed against each other. And I think they knew certain metals, when set up in a conductive environment with like electrolytes or wiring, could generate power over some time as seemingly chemical changes were happening. So on the left of this diagram, we have a high voltage circuit set up, maybe by, again, two metals with differing voltage. And we have a cathode and an anode in there. And from the cathode, I think rays of some kind of radiation were released. And scientists discovered this and were aware of this and shared different findings about it. But it was not well known what kind of rays or radiation was being released from this cathode ray tube. So Thomson here decided to do some experiments on it. He would shoot it through several different things. There's an area in the middle here that has magnets, south and north pole, creating a magnetic field, and also charged plates, creating a sort of negative to positive gradient as you go up. And he was able to analyze various different atoms and ions going through here and build up some knowledge of how they would hit a detector. And generally it was found that the more charged something was, the more it was affected by this electric field between the charged plates. And by more affected, I mean more deflected in some direction. So positive things would be pushed down on this diagram. Negative things would be pushed up. But he also found that the more seemingly massive particles would not move or not be deflected as much as the less massive particles. And if you know something about physics, you'll know force equals mass times acceleration. So that kind of makes sense. You need a greater force to accelerate a more massive object in some direction. And so he tried with cathode rays to put them through this electric and magnetic field, and he found there was a deflection towards the positive plate side, and it was a fairly large deflection, I think, indicating there's significant charge on whatever this is. But when he considered the mass of what was hitting the detector, it was seemingly very, very low mass, like almost 2,000 times less than other types of particles. I'm not sure if he was able to do this with like protons or alpha particles, but generally other atoms, and it would have been much, much less than whole atoms, like thousands of times less massive. And yet, it was so charged, like it had the same charge as a chloride minus ion or something, 1 minus. So this was a pretty crazy discovery. The mass to charge ratio in terms of its charge was so huge, but it seemingly had very little mass. What could it be? Well, it had to be something new, a new kind of particle that people hadn't really considered before. And I think he called it some weird name, but later on scientists changed it to the electron. And one of the really important things from this experiment is he would generate these cathode rays from particular metals or elements. I don't think they had to be metals, but in the cathode. And he could change the materials of the cathode and still produce cathode rays, and they would still generate the same results on his detector, the same mass to charge ratio. So he had to conclude that, all the elements that he could make his cathode with contained whatever this small negatively charged particle was. And that led us to the assumption that all atoms contain electrons, and electrons are sort of fundamental. They're not different as you move from atom to atom. They're just electrons. Okay, so I don't know if I explained that well and probably said a couple things that aren't true. You can go read about it yourself if you're interested, but on a basic level, I think that's how this experiment worked. And again, I'd recommend you come back after you learn about electric and magnetic fields in physics, and you learn a little bit more about mass spectrometry in chemistry. All right. So after we discovered the electron, we needed a new model of the atom. It's not just a ball or a sphere, but if there's negatively charged particles in it that we can shoot out with a cathode ray tube, and yet atoms on their own are neutral with zero charge, there needs to be some kind of charged balance going on inside the atom. So there's the idea of the plum pudding model, or the cookie model, that Thomson proposed. So the atom, a sphere, mostly of positive charge, but inside very low mass little chunks. You can think of them as, chocolate chips or something in the cookie model, but they are negatively charged and low mass and sort of dispersed evenly through this structure. So I think this gained some popularity and caused some discussion, and people wanted to do further experiments. So we get to the nucleus discovery, generally by Rutherford, the scientist. So his experiment was to shoot what are called alpha particles. Again, this is jumping a little bit ahead in our knowledge of nuclear chemistry and physics, but I have a little diagram here in the bottom left of what an alpha particle is. It's essentially a helium ion, a helium nucleus that has no electrons, but a helium nucleus has what are called 2 protons and 2 neutrons, and it has a 2+ charge. So he developed a kind of box with radioactive compounds inside that would constantly release these alpha particles. So they're kind of massive, they have quite a high positive charge, and they would be launched out at high speed. And he did calculations and predicted that these alpha particles, with the energy that they had, should punch through atoms and just travel in a straight line. And he made a very thin gold foil, put it in front of this alpha particle launcher, and wanted to test this theory. Again, he expected the alpha particles would punch through the cookie model atoms and just travel through, and he would detect them on the other side. And generally that is what happened. And I should say his calculations were based on basically charge density, I think. He knew how much charge should be in an atom in the cookie model and in a gold atom. And, the density at any one location should not be enough for the positive charge to repel the positive alpha particle. And yet what he saw was 99% what he expected, and then about 1%, or slightly less than 1%, were deflected a little bit at some angle and didn't travel straight through. And then some small percent, 0.1 or less, actually almost got reflected right back where they came from. And this is really surprising results. You might say, well, 99% is what he expected, but his math and modeling could not account for that other 1% that was deflected. And that's important enough that the theory had to be revised. And so I have a diagram here on the right as well that shows, zoomed in, kind of what must be happening here. So most of the particles just travel through. Again, I have a few lines here showing going straight through, but this is really 99% that just travel straight through. And then I have a couple deflections shown here. So some are deflected a couple degrees, maybe 10 or 15. A couple are deflected like 120, big angle, and a couple are reflected 180, going all the way back to where they came from almost. So the cookie model could not explain this. There shouldn't have been any regions of positive charge density and mass that were enough to deflect alpha particles. So it must have been true that there were some very small areas with super high density of positive charge. And 99% of the time, our alpha particles don't hit those, but small percentage of the time, they do, and they are deflected or reflected. So this was a huge idea, and I think they did further experiments to really show and prove this and further mathematical calculations. But generally, it was accepted that the positive charge in an atom is concentrated in a small area in the center, and most of the atom is empty space. So in summary, the knowledge gained from this experiment is that the nucleus is very, very small compared to the total atom size. The nucleus is very positive, and the nucleus contains most of the mass of the atom. So I have a little generated image here from ChatGPT showing nucleus concentrated in the center, so it contains most of the mass and all of the positive charge of the atom. And that's 10 to the minus 15 meters roughly of diameter. And then the whole mass of the whole diameter of the atom is 10 to the minus 10 meters. So you can tell right away this is not to scale. I tried to make a slide where it is to scale, but it's not possible, okay? This is a 10 to the 5 difference, which is like 100,000 size difference. And, you know, if I tried to make visible pixels on a slide here, I would not be able to then show the actual width of the atom. That's how much of a difference in size there is between the actual atom and the nucleus size itself. So be aware, this is a visual representation with the numbers written, but this is not to scale. So then Rutherford introduced the planetary model, which is something you might be familiar with. It's often used in like sciencey artwork and things like that, where we have a positive nucleus and negative electrons orbiting that, kind of like a solar system with planets and a star. We would really like the atom to be like that, because that's something we can relate to and we can have an analogy for. But one thing you'll notice about this model is that none of the electrons are particularly special or unique. They're essentially all the same. They're just orbiting at different angles, but their distance and energy and speed and things like that, I think, was generally considered to be equivalent to each other. But very soon after, I think one of Rutherford's students, Niels Bohr, did further experiments. And what he found, I don't know the details of this experiment, but he found that, you know, as you knock off or add electrons to different compounds, different amounts of energy are required to do so. And that means each electron is not the same. It doesn't exist in the same zone or have the same properties. So we had to modify this sort of all electrons are equal idea into electrons are different energies. And through a lot of experiments and calculation, generally we propose that electrons can exist in these main energy levels. So I've shown a diagram here generated from Cloud AI, but we have a level 1, level 2, level 3, level 4. These are written with n equals, so n equals 1 or n equals 2. So here's a carbon atom. It has 6 electrons, and sort of 4 of them are kind of in the same level in level 2, and then 2 of them are in level 1. And even though there's nothing in level 3, 4, 5, 6, 7, we imagine that these levels exist, and if you give this carbon a bump of energy in some way, you can knock some of these electrons up to those higher levels. Experiments were done to show that, and we'll talk a lot about that in future videos. So now we have a similar planetary model, but this one has different levels, very much like planetary orbit radii, or the radius of a planet's orbit. You know, Earth is different than Jupiter, is different than Saturn in terms of the radius size. And in terms of atomic energy levels, it has to do with energy as well. All right. So, shells contain negatively charged electrons. But we didn't finish there. I think quite a few years passed, and we got into the era of quantum mechanics. A whole bunch of discoveries about the microscopic scale were discovered. Things like matter can be waves, and everything is probability-based, chance-based, instead of deterministic. But we'll try to just go over some of the basics here. So Schrodinger proposed that instead of electrons orbiting around a nucleus, they could exist in zones of probability. So I have a diagram here showing the nucleus, again, in the center, as always. Very dense, positively charged, massive zone. But then around that, we have areas with certain chance that you might find an electron. So maybe this dark orange area, within that zone, we might say there's 80% chance of finding the electron. We're not even going to distinguish exactly where it is most of the time. We're just going to say it has a chance to be in this zone. And then maybe the slightly lighter region around that. So if we go from the nucleus all the way to the edge of that lighter region, we might say, well, now we have a 90% chance of finding the electron in this slightly wider zone. And so you might say, well, the difference between these, or the chance of finding an electron in the lighter zone only, is about 10%. You know, these are kind of the discussions and proposals of Schrodinger and similarly interested quantum mechanics scientists at the time. And so as you get further and further away, you eventually get to 99 or nearly 100% chance to find the electron. And beyond that, you can say you have almost no chance to find the electron. And that's kind of considered outside the atom at that point. So you'll often see atoms drawn as like spheres or balls. But this new proposal says it's actually sort of a spectrum of probability as you move away from the nucleus. There is no fixed edge of the atom. But oftentimes when we look at those visualizations of like a sphere or something, you have to imagine that that's representing 90 or 95 or 99% chance to find all the electrons within that volume. That's how we can take Schrodinger's proposal and discoveries. So I also just want to mention in the top right here, I think mostly this was de Broglie, or de Broglie, as you might read it, Debrogie, who proposed that matter, including electrons, we know electrons have mass, but he proposed that they may also have wave properties. And as they exist in certain energy levels, they can exist as a kind of standing wave. Again, if you're taking physics, you'll learn a lot about this, but you can imagine it just like a string that's vibrating up and down. And if you imagine an electron in this way, you would not necessarily consider it to have a fixed position, right? This is a wave that's just oscillating in a particular zone. And so we sometimes do have to think about electrons in this way. And I've shown what might be considered a hydrogen atom on the left with the Schrodinger model, but that's a simple sort of first level shape that you might find. In the bottom right here, I have various other shapes. There are things that look like dumbbells or peanuts, as well as pinwheels and weird donut shapes. All of these were generated due to Schrodinger's equations, wave equations for different energy levels, and as they are called, atomic orbitals. So we will learn quite a lot about this later on, but just for now, be aware that these came about due to mathematical calculations, very complicated things with like differential equations, and perhaps I'll show you in one of the videos what the actual wave equation is for a hydrogen atom, and we can see how complicated it is. But for now, I think that's a decent enough introductory explanation. So we had this progression of models, right? The Dalton sort of element proposal, maybe it's a ball or sphere. Then we had the Thomson pudding model, the Rutherford planetary model, the Bohr planetary model, the quantum mechanical zones of probability, chance of finding an electron model. And then what's next? Well, maybe that can be your job to add or discover new theories. The ones before this were not the end, so maybe it's not a good idea for us to think that the quantum mechanical model is also the end. But I will say the quantum mechanical models are super powerful. If you go to university and you have a chance to use supercomputers to generate atomic orbital shapes like this, generally you'll send, your request to some supercomputer, maybe in another country, and they'll try to use the wave equations to generate shapes and bond angles and molecular radii and size and things like that. It takes a few hours and a lot of computing power, but the predictions that these can make are extremely good. You can predict what a molecule that's never been made before will look like and its different properties. And when it actually is made, I think it will agree very well with computational predictions these days. So that's really good evidence that the quantum mechanical model is powerful and close to reality anyways. So further on, John Chadwick, I think was his name, and this was a scientist who also did work on different substances and elements and radiation types. So he also had an alpha particle generating box that shoots a beam. He would launch it at beryllium, specifically beryllium-9 atoms. And he got results from this. He got that carbon was produced, but also some form of radiation was also launched out of the carbon, or out of the beryllium that was bombarded with alpha particles in this experiment. He wasn't sure what this radiation was at the time, but he knew that it had no electric charge. He would put an electric field around the radiation coming off, and it had no effect. The radiation was not attracted or repelled by any positive or negative regions. And when he put a barrier of paraffin wax, which is just some carbon and hydrogen-based waxy solid, he detected that protons were actually released out the backside based on their charge and mass and energy. And that was really surprising, because to knock a proton out of, various carbon and hydrogen atoms that are in the wax would have required a ridiculous amount of energy. And he proposed maybe this was due to some radiation types like visible or ultraviolet or X-ray or gamma ray radiation, but none of those even would have enough energy to pull a proton out of this wax paper. So he proposed that maybe it was actually a physical collision between a particle. This particle has no charge, but when traveling at high speeds, it could knock out protons from this paraffin wax paper. And so he proposed that this is a neutral subatomic particle called the neutron. The neutron has about the same mass as one proton and no electric charge. And so I have not a chemical equation, but a nuclear equation written at the bottom here. An alpha particle, which is a helium-4, 2+, nucleus that interacts with beryllium-9. It produces carbon-12 and 1 neutron. And you'll see that the masses have to be balanced there. If you look at the numbers just on the top rows, you have 13 mass in the starting materials, and you have 12 plus 1, which is also 13, in the products. This is a nuclear equation, which you will learn about in IB physics if you're taking that class. So, neutron was discovered, and it's proposed that that is also a subatomic particle existing in almost every nucleus of most elements. So let's talk about the mathematical scale of particles a little bit. Length. Atoms are unbelievably small. They range from about 1 times 10 to the minus 10 meters to 5 times 10 to the minus 10 meters. And the units commonly used to express atomic dimensions are the picometer, Again, if you watched my science and math communication video, you'll know that's 1 times 10 to the minus 12 meters, written as PM for picometer, or the angstrom, big A. And I think that A usually has a little circle on top to represent the country or the scientists who actually discovered it. It's not a pure English A. Anyway, so an angstrom is 1 times 10 to the minus 10 meters, which is quite often used, I think, in X-ray crystallography and other types of distance measuring where we're looking at the atomic scale. Then what about mass? So we should learn an atomic mass unit. So one atomic mass unit has an equivalence in kilograms, 1.660539 times 10 to the minus 24 kilograms. We call that the atomic mass unit, and sometimes you'll see this just written as U instead of AMU. And we have one electron, which has a certain charge as well. So we do have to consider electric charge. If you remember from my math and science communication video, the SI unit for electric charge is the coulomb. But 1 coulomb is a huge amount of charge. Like people who are measuring big currents going through wires were measuring 1 coulomb. So 1 electron only has 1.602 times 10 to the minus 19 coulombs. Very small amount of electric charge. But it is kind of the fundamental unit of electric charge. So we often just label it with E, like 1E or 2E or 3E to represent different amounts of electrons worth of charge. Okay, just to expand on the mass a little bit, we can look at the subatomic particles that we now know of. Proton is about 1 atomic mass unit. I say about because in some sense it's different in every atom, every nucleus that it's found in. And it's defined based on the carbon-12 nucleus. But in general, we can say a proton is about 1 atomic mass unit, and it has plus 1 charge, which is an E worth of charge. So it's 1.602 times 10 to the minus 19 coulombs. Its location is in the nucleus. Neutron then is also about 1 atomic mass unit. I think it's slightly more than that. It has 0 charge, and it's also located in the nucleus in that very dense and massive central region of the atom. An electron then is much, much lighter or less massive, 0.00054 AMU. That's about 2,000 times less than the proton or neutron. It does have a minus 1 charge though, even though it's such a small mass, and it's located in the electron cloud, or that zone of probability that we discussed in the Schrodinger model. All right. Element nuclear notation then, this is a very important thing. An element's nuclear notation must have its mass number, A, its atomic number, Z, and its element symbol from the periodic table, X. And then we would write it this way, X as a big symbol, top left A, bottom left Z. So A is the mass number, it is the protons plus neutrons number. Z is the atomic number, that's protons, and star electrons, because in a neutral atom, which has no net charge, or its charge is 0, it must be true that the number of electrons perfectly balance out the number of protons. So Z is often the number of electrons as well, if you have a neutral 0 charge atom. X then is the element or particle symbol from the periodic table. Now I do want to introduce the idea of ions. I've talked about these in previous videos, but officially defining them here. So through collisions or interactions with radiation, atoms can lose electrons. This is known as the formation of a cation, which is positively charged. You really have to remember this vocabulary, especially for IB exams. So the way that I usually remember this is that cats make me happy, make me positive, so cations are positively charged. Next, some atoms are more energetically stable when they gain extra electrons. This could be free electrons that they pick up as they move by, or could be stolen from nearby atoms. When this occurs, the result is called an anion, which is negatively charged. So anion, negatively charged atom, cation, positively charged. Both anions and cations are charged atoms. They are known as ions. Okay, hugely important that you start to remember which is which and use this vocabulary in your explanations. So we also have ion nuclear notation. It's just building a little bit more on element notation. So now we have its electric charge Y in the top right. And the charge will either be due to lost electrons, then it becomes positive, or due to gained electrons, then it becomes negative. Be careful not to mix these up. It might sound like gaining something is positive, but electrons are negatively charged, so as you gain them, your charge goes down, more negative. So here's some examples. An oxygen 2- anion. This has gained 2 extra electrons, but it's a very common anion. So O, 16 mass, 8 atomic number, that means it must have 8 neutrons, and 2- charge, that means it must have 10 electrons. Gained 2 extra for 2 extra negative charges. We could also have a chloride anion, Cl, with 17 protons, 36 protons plus neutrons. So I think it has 19 neutrons and a -1 charge. And so it's gained 1 extra electron from somewhere, also a very common anion. What about a cation? We could have beryllium 2+, beryllium 9. Beryllium has atomic number 4 protons, and 5 neutrons will make its atomic mass 9. And then 2+ means it has lost 2 electrons. They've gone away somewhere. We don't exactly know where without much context, but they are lost. So it's a good exercise to try to count how many electrons, how many protons, and how many neutrons are in these examples, or anything that you can find in your textbook or online. And you'll notice that the sign on these comes after the number of the charge, right? We don't write -2 or +2. We write the number and then the sign. And I will say, for the chloride in the middle, whenever this number is 1, it's very often not written. It would just be Cl with a minus sign in the top right. And you should do the same. It's possibly going to be marked wrong on an IB exam if you write the 1, so just be aware of that. Alright, and that brings us to an end. This video is almost 45 minutes long, so I think that's a good place to stop for now. Hopefully you've enjoyed my sort of basic explanation of these experiments and how we got this evidence. If you're interested, I really do recommend you go look up the specifics of each of those experiments and find out the details, especially after you've learned other things in the chemistry and physics courses. Anyway, next time we will do isotopes, the idea that different atoms of the same element can have different numbers of neutrons and different total mass, and consider what the effects of those are. Alright, thanks. See you next time.